You had to fight the borrow checker day. It was right. Surprise, surprise. I thought you said, the first time I read that, I was like, I was right. Surprise, surprise. I was like, you were right and the borrow checker was wrong. That seems like a once in a lifetime event. Uh, looking forward to your contributions to the Rust compiler then. Can we check off game of life problem from the list of to-dos? Is this the game of life one? We're not even at that point in our stream yet. We still have to cover what the actual F I did yesterday. So do we need a recap of like the problem and stuff? We should probably do a quick one, right? No, Alfred, come on. No, Alfred doesn't want to pop up. Alfred's just not going to come with us today. That's fine. Whatever. We'll just hop a new Chrome window onto a random desktop for no reason. Maybe it's my keyboard that's not working. Maybe it's not Alfred. My keyboard working? No, it is. Oh no, there's Chrome. Whatever. We already have Chrome. All right, that's day 10 here. So day 10 was this problem with these little thingamabobbers, right? So each line is either invalid or valid. And actually, more specifically, these lines are either corrupted, as in they are completely invalid, or they are unfinished. So part one was find all the corrupted lines and get the like the thing in the input that made it corrupted. We did that straight in Nom. That was, I don't know. It's probably, depending on how you wanted to do it. Like if you were going to do parsing for a programming language, you would probably want the parser to survive as much as possible. So splitting it up into different lines, calling out errors on different lines that were like, hey, this one doesn't parse or whatever would probably be useful. Being able to point to specific spots is probably useful. And for that, we did everything inside of Nom. So this process part one function is literally just map over, parse the chunks out, deal with whether we had an error or not. And if we had an error, it gave us back the character we needed in the spot that we needed it, and then we scored it and whatnot. We did that through a reasonably, actually looking at this one, it's much simpler than part two. Oops. So we did that through a recursive nom parser, basically. And I'm going to show you the dat heap profile in a second. But the dat heap profile is really interesting. It's very different than anything else that we've done so far. So we look for the open bracket. If we can parse a closed bracket, we parse it. And then that means that we're at the bottom of the, like we've got a curly brace and a closed curly brace right next to each other. If not, then we basically go through and parse as many chunks as possible because there can be multiple next to each other. And then, why did I loop here? Right, I'm looping here because there can be multiple side-by-side chunk matches, right? So many one can succeed, and if many one succeeds and we're left with an open brace, we need to dig further deep into that and let chunk do its work so that we can get out the actual length of input that puts the offending character at the beginning. So If we just do it this way, then the many one fails. But really what we want is chunk to succeed once and then fail once. If there are two side by side and the first chunk succeeds and the second chunk fails. So that was that. And then we passed back the characters and it was all good. And that ran. That runs in a DAT heap profile of 160 kilobytes. So fairly large. TG max is only 11 kilobytes. So maybe something worth looking into there. I'm not going to do it on stream today because we're going to do problem or day 11 instead. But it runs in like 280 nanoseconds. Allocates 160 kilobytes. The input file here is about 11 or 14 kilobytes, if I remember correctly. The input... let's pivot this. And we get 10 kilobytes, 10.3. So at TG max, we have a little bit more than 10 kilobytes. So we're doing something here. I don't think I used references very much, especially in part one. See, tags. Many one is a vec allocating function. So we might not even need to do that because we don't actually return. So chunk doesn't return anything, right? Chunk returns unit, chunk returns unit for a successful parse for part one. So many one allocates probably a vec for no reason. So we probably could get rid of that. But if we run this, we can take a look at the DAT. Because the DAT is actually really interesting. Let me refresh this because that's part two right now. So the DAT heap profile for part one on day 10. You'll notice as we scroll down here, the tree just keeps getting deeper. Right? And I think this is the sign that we have the recursive function, that is, right? So it just keeps kind of like going in and going in and going in, which means we've got like a vec, a vec, a vec, a vec, a vecs. And I think all of those are getting copied out. So because we don't return any actual usable parsed value here, I don't think we need to do that in part one, right? So in here we can see there's the chunk parser for, it says day 5. It's not day 5, it's day 10 because I forgot to update the label. But the chunk parser just runs a ton of times. And then that comes back out into a vec. And the vec is not small, I suppose. And we do that for every line, right? So that ends up being 150 of the kilobytes. So if we can fix that a little bit, that would be nice. And then there's this other one that's 8 kilobytes, but like we don't really care about 8 kilobytes compared to the 150 or whatever. This is also the many one, but I think it's the later many one. It's not the first many one. The first many one is the problematic one. But you can see how in the heap profile, basically we keep going recursively down, which is really interesting. And I think that changes with part 2 in terms of the depth of that. So let's go to part 2, because part 2 was the part I was doing on stream after that. And it's probably the part you're all interested in. We don't need this error tree stack thing here. Let me get rid of a couple of these debugs before we... So process part 2 does basically the same thing part 1 does. It applies chunk 2. Well, chunk 2 is a new function. So we had chunk in as the parser for part 1. Chunk 2 is the parser for part 2. And basically what we do here is we try to parse the chunks recursively out. And it's possible at the top level that we can have like one line that has a successful chunk and then a failing chunk. So that's why we loop here, because we really only care, like if we parse a successful chunk and there's more input left, right? If input length is greater than 0, then we should try to parse another chunk. If we get an error, then we just return the error. And if you've never seen like loop break before, loop is an infinite loop and break lets us return a value. So we can return OK from inside of our loop to the outside, and loop again is an expression, so that returns from the map. And then down here, we're just doing the math on the successful parses. So let's talk about what I actually did here, because what I was doing on stream was probably hard to follow, right? What I was doing on stream was I was trying to build up what was effectively this AST struct, but without storing anything anywhere. And that made everything kind of really awkward. So I backed out for a second. I built the actual AST struct here, where we have a left car, a right car, and any of the children. So whenever we have a chunk, this could be called chunk, right? With a capital C. And probably should, thinking about the parser naming now. But we have like the open bracket, an optional closed bracket, and any of the chunks in the middle. And the important part is that this right hand side, the closing bracket, is sometimes there in the input and sometimes it's not, right? So if it is there in the input, then this is going to be some car, and if it's not there in the input, then it's none. And when we go to look at chunk 2, it's basically the same parser we wrote before. So we could probably pull these parsers together into being the same parser. We were just so focused on the error case in the first one that I wanted to do it as a second one so I wouldn't mess up both of them at the same time. But basically we look for the opening, right? We look for the closing like we did in part 1. If we have the opening and the closing, we're done. And the return values here become the open car. If we have a closed character, it goes into the AST. And then we have children. And in this case, we don't have any children because we have open car, closed car. In this case, we have an open character, but we failed to parse a closing character. So we don't have a closing character and we don't have any children. In this case, we are reapplying chunk 2 in the middle, right? In the middle is the children. So when we build our AST value, what we end up with is an open car, a closing character, and the children in the middle. And then finally, in the case of incomplete, which is we didn't get to, like, the input ran out, we obviously don't have a right-hand side character. So we have the open, so we end up with this AST that's a recursive AST that basically contains not copies, it contains itself as children in a vec. So you can see the AST type at the top, you can see the AST type in the children. And then the really kind of interesting parts here are we get that AST value out of the parser. So we parse everything, right? We parse everything. It's all valid if it's valid. It's all valid if it's incomplete, right? And we've built our data structure in a way to support that incompleteness, right? The right-hand side doesn't have to be there as long as the right-hand side isn't the wrong character. So when we get this back, we immediately two-string it because we need to get basically all of the trailing pieces. It contains itself. How do you avoid the unknown size of compile time? Is the AST an option? The AST is in a vec, so the vec could be empty. And vec puts AST on the heap anyway. So children is always like a pointer to data on the heap. Like vec is an owned type, right? I used owned types all the way through here. None of these are references. We aren't just storing directly an AST inside of an AST infinitely. This is basically the same as having, like, if this was option AST, we would only be able to have one AST there. But the reality is that we can have multiple, so it's a vec instead of an option. So the really interesting part here, aside from the parser, basically the lesson here is that when we're doing the nom parser's job is to build something up, right? And in our case, we built up this AST. And that allows us to then take that AST and either validate it or print it out however we want. And like we can operate on that tree now. So we're taking something that is just a line of characters and we're turning it into a data structure that we can operate on. So when we go to display AST, what I did here, this is kind of like a pathological implementation of display. Like it's probably not what you would want if you were actually displaying this. But I did it for convenience anyway. I could have done a different trait. I could have done this as a separate function. I didn't. Shrug. So we use write, which takes the formatter. So basically if you write format or print line or whatever, you have to write to a formatter, it formats the results, and then it prints them out or whatever. We have two values here. One of them is all of the children, which calls toString on the children, collects them into a string, and then prints them out. So that uses the same display because display is given us the toString implementation basically for AST. And then if we don't have self.write, which is the closing character, then we match the opening character and we print the closing character out, right? So what we end up with here is no printout for anything that is either a left value, which is always there. Like we never lose out on a left value because the only thing we have to do is close. We print out all of the right-hand sides of the children because that's what we're doing in this display trait. And then we print out the right-hand side of the current AST that we're working with, but only if it was missing. So if it was already there, we don't print anything. So in this way, what we actually end up getting is, if we look at the day 10 code, what we actually end up getting is a string that is this ending. That's just the closing characters. So when we do this toString, it's calling that display implementation. We get just the closing characters here. And then we go over them with cars, which creates an iterator. We fold, we start with 0. So ACK is 0 in the beginning. We have to multiply by 5 and then add a number based on which character it is, right? And that just works. And then we sum it up. At the end, I sort it. I pick the middle one because integer division goes down to the middle value. And then we're done. And that's it. So the big lesson for what we were doing with nom yesterday is that parsers are meant to build up a structure, right? It's meant to eat the thing and build up the structure. And if you can eat the thing and build up the structure in a way that allows you to keep going even when there's incomplete data or something like that, it makes life easier, right? Because we still have the failures, right? They still fail if they aren't the right characters matching. But what we end up with in the parser at the end is a data structure that supports incomplete values. So nom isn't really the focus here. It's the data structure that has to support that. And as long as the data structure supports that, nom gives us the combinators to actually parse those that data out. So hope that was useful. I'm probably going to stick that on the end of the day 10 video. CP R day 10, day 11. no way I could code that. I think you could, you know. I think the difference is if you can write a nom parser, right? And this is kind of what I was trying to get at. If you can write a singular nom parser that builds up into some data structure, any data structure, like just say struct something and you parse nom out into that. It has nothing to do with nom from that point forward, right? The data structure either requires that you have all of the data or it can be incomplete, right? In this case, it was pretty simple. It was left bracket, right bracket. So if we didn't see a right bracket, we just set that to none. But I think that that understanding that the data structure has to support what you're trying to do, and then the nom parser is just any regular nom parser, is the key insight there. Okay, so let's get back into library here. Let's get rid of all of this stuff. I wrote a bunch of tests yesterday too. So if you're interested in seeing the tests and display and the impls and stuff like that, it's all sitting there. Wow, we wrote like 150 lines of tests yesterday. Okay, so we have a thing. I think today is going to be an ND array day. That's what it looks like. Basically what we end up with is this board. So I think this is the test input. We'll pull this into test input. And then my understanding of this is that the numbers are from 0 to 9, basically. And if you, so there's step 1, and then there's step 1 part A. Step 1 part A is to add 1 to all of these numbers, which we can do with ND array. We know we can. We can index commute over everything. Then we have a pass to detect if there are any 9s. If there are any 9s, we can use windows over the whole thing like we did the other day with a padded board here. And then we just update everything +1 if it's a 9. And then we just loop that over until we don't have any more 9s to process. And then the values that we have that are over 9 get reset to 0, and then we start the whole thing over again. So for example, before any steps, if you have like this thing right here, then all of these in the middle, except for the middle one, get cranked up to 10, which means they all flash, which means that this goes up to 2, and then this 9 takes it up to 3 because it's next to it, and so on, and then you end up with this, basically. So I think this is gonna actually be reasonably okay for us. We're gonna do just fine on this first test. I'm gonna directly just go and grab immediately. We have which day was it that did numbers? Was it day 9 that did the same kind of thing? What's the test input for day 9? It is day 9. So we already wrote this. We've got rows and we've got the puzzle input, and I'm just gonna grab this, and this is gonna be the exact same thing. Like, I'm not even playing. This is, we already wrote this. There's no reason to. We aren't using most of this anymore. We'll skip error tree. We aren't using we aren't using complete and the other thing, so we'll get rid of that. Let's pull in complete new line. So this is what we end up with. I think U8 is going to be able to hold this number because I'm going to use an enum, actually. So I think we're going to, let's grab this puzzle input piece and we'll stick this in process part 1. And this is not a height map. This is squid map. And squid map, I think, is the 2D array. Yeah. So that's it. We're good. We now have the same thing we did the other day. We have a padded board with X's on the outside. Well, actually, is this the X's one? Yes, this is the X's one. I think I want to change this though. I think to make this easier, we're going to do enum squid. Needs flash. Flashing. Flashed. Energy. And the energy is going to be a U8. Is that everything we need? Is that all of the states? We either have no squid, right? Which is basically none. So all of these none padding values are going to be no squid. The energy values are going to be the values from 0 to 8. Needs to flash is going to be when the value gets over 9. I guess we don't need to do that. Right? If it's flashed, we don't care about the U8 anymore. It's over 10, right? If it needs to flash, then it is 9 or higher. Or actually, is it 9 or higher, or is it over 9? Let's go find the rules. Any octopus with an energy level greater than 9 flashes. So greater than 9. So if energy is greater than 9, then it needs to flash. I guess this can be a function, actually. Impulse squid should flash. Takes a reference to self. And this returns a Boolean. Did I mess up? Oh, FN. I was like, this should work. Should flash. If self dot if let squid energy X. Can we do it right here? I feel like there's a really easy way to do this that I'm missing. Like a match self. Like, let's get rid of all of this stuff so that Rust Analyzer can... Right, there's this stuff. And then we have everything else. And this is a true. What's wrong with 9 there? Expected a reference to a U8. Found integer. Really? That's your problem? Okay. Fine. Okay, so we have a failing test. We have should the squid flash, which is the function that we're going to use as we iterate over all these squids, whether it's flashed or not. So if it should flash, we need to change the internal representation of the squid to flashed. And if it's no squid, then it's no squid. This is squid, no squid. This is squid energy. This is just squid. This is squid, no squid. This is all squid. We don't put clone on squid, so we're going to run into a couple of trade implementations here. So here we do derive, clone. I think that's going to be the only one we need for now. Maybe we need something else like copy for the array. Found enum option from shapevec. I didn't change the type here, so this is going to be an array2 of squids. Okay, so we have a bunch of squids. We have a squid map. A map of squids. So, let's do squid dot, what is it? Dot in, we don't need indexed. We just need to, why can't this figure out that this is a thing that has the indexed iter on it? Right, nd array. Array base, index, indexed iter mute, I think is what we want. For squid in, all these squids deserve a whole section of an aquarium IMHO, a squid ward, if you will. That's pretty good, Nikki. I like that. Let's do squid. That's why I had needs to flash here. Because this is going to be FN tick and mute self, and it's not going to return anything. And this is going to be match self.energy x. If x equals 9, then we and mute needs to flash. Why? Then we self equals needs to flash. Let's do this instead, actually. Else x plus equals 1. What did I mess up? I messed something up. That should work, right? Otherwise, we do nothing. So if we have, I guess, a flashed squid or a needs to flash, let's not call this increment energy. We'll call this increment energy. So down here, we have squid dot increment energy. This is squid map that we're doing the indexed array over. That's why it wasn't working before. We only care about the squid, so we increment energy and then loop. Let done equals false. Let flashes, maybe let mute flashes equals U64. Let's just make it some massive thing here. So we increment it, and then actually I think we need to move on to another loop. What is wrong with this iter? Cannot borrow is mutable because I didn't do mute here. Yep, there we go. And that will run forever because I'm looping over infinitely. Oh yeah, just holding my body up for hours and hours a day while streaming is a lot. So we had the squids, we increment the energy on the squids. This whole thing is going to be a step. So we are going to have to loop over this as well. Right? This is going to be a loop. For, I don't know how long we're going to loop for, but we're going to loop. We're going to iter. And then we need a second loop that goes over all of the squids in a windowed form. So we need to do Windows 3.3. We do need mutable access to these. So this will be fun. How did we do it the other day? We did Windows. 3 into iter, and then we just filter mapped on them. So we didn't do mutation here. So I mean, like, we could just keep returning like the new map of squids. That's an option. I think that's actually the better option, but I'm wondering if we can even do mutation through windows. So I'm going to try to do mutation through windows for kicks, basically. For squid in squidmap.windows. Squid box. Squid box. What is it? 0, 1, 1, 1. What's wrong with that? Move occurs. Squid map, not squid box. Wait, it is squid box. What am I doing? Oh, borrow the squid? Yeah, we can borrow the squid. That makes a lot more sense. So we've got the central squid. We need to check to see if this squid needs to flash. Right? So match central. If it's flashed, we do nothing. If it's got an energy level, we do nothing. If it's no squid, we do nothing. So this is all nothing. If it needs to flash, so maybe we do if we still need the squid though. Let's do, we're gonna have to do our mutation here anyway. Central equals squid flashed, right? And this is going to need to be a mutable reference. Which we are not going to be able to get because we don't have this. Squid can't be dereferenced. That's not really the point here. Cannot assign twice to a mutable variable. Cannot assign twice to a mutable variable central. Yeah. I think this still needs to be a mutable reference. Is there a Windows mute? That's a great question. Doesn't look like it. We could get mute for each of them. right? So if we do like something like this, this one will always exist, and then we get a mute squid. But get mute on squid box is a problem for what reason? Data mute is not implemented for view repr squid reference. So now we start getting into a little bit of if we had Windows mute, I feel like that would solve our problem really easily. Squid box doesn't give us the indexes into the original. So it's possible that we don't have the opportunity to do this. We do need to Windows and we need it to be mutable. This isn't a thing, is it? No. From iter, indexed iter mute is a thing on an array base. It may not be a thing on Windows, which is really going to be the problem. Yeah, it's not on Windows. Yeah, that's because we chose to go with the mutation, Nikki, because I thought it would be more interesting. So Windows. Borrow, mute, blanket implementations, auto trade implementations, raw dim into iter. Clone from clone. It's interesting, right? It seems to almost not want us to do mutation through this. Which, like, theoretically is fine, right? But what were we doing the other day? We did Windows, right? Into iter, filter map. And then we got each of the points. We filtered them all down and then changed the current point +1. So we didn't really need mutation in the other day. We do have a mutable squid map. Can we iterate over the mutable reference here? I think you can make slices mutable. We do need the windows though, because we do need all of the neighbors, and Windows makes that so easy. So I would love to use Windows here. Squid doesn't implement copy. That's fine. We don't need it to. Cannot borrow squid box as mutable. Why can't we borrow as mutable? Cannot borrow data in an index as mutable. Index mute is required to modify index content, but is not implemented for array base, view repr, and squid. There's something else about this that we need to do. You can use slices to redo what Windows is doing. That's interesting. Array base, view repr. Yes. So these types here are immutable types, right? Well, not immutable, but they're shared reference types. Like it's a shared reference to a squid, which is not what I want here. I think it's a shared reference to a squid because Windows can only do that. Where's Windows? Windows is here. Let's look at the Windows function. Returns a Windows. So it looks like it'll just pass through everything actually. So if we can get the mutable reference into Windows, then we might be okay. Into iterator, AD. An array view. Can an array view be mutable is a question. This is a read-only array view. So we need an array view mute version of Windows. And here, the item has to be an array view. And I think the only difference between array view and array view mute is going to be the reference inside of it. So array base view repr shared reference, array base view repr mutable reference. So that's the thing. I think if we can figure out how to convey to Windows that we want mutable references, that this should work. Because this type here is being inferred from somewhere. So squid box is a view repr shared reference to squid. This doesn't change anything, so Windows isn't pulling from that. For mute squid box, doesn't change the interior type, right? Up here, we're storing owned types. So squids, right? Here we get mutable references to a squid because indexed iter mute gives us back that. We can get mute squids. Can we force this? array base view repr. This isn't the full type. Array base view repr squid dim usize 2. Dim usize 2. Is that even view repr mute squid dim usize 2? I think all of that matches. And this needs an extra for the type argument there. And this is going to yell at us because of syntax. Not because we got something wrong. So let me just array base, view repr, and mute squid, comma, dim, usize 2. Okay, so if that was going to work, it would have worked. So you think we should do slices instead of windows? And then we can potentially do mutable slices? Slicing, slice mute. Slicing arguments can be passed through the macro s, which will be used in all examples. The explicit form is an instance of slice info or another type which implements slice arg. See their docs. If a range is used, the access is preserved. If an index is used, that index is selected and the access is removed. This selects a subview. When slicing arrays with generic dimensionality, creating an instance of slice info to pass to the multi-axis slicing methods like slice is awkward. In those cases, it's usually more convenient to use slice each axis. It's possible to take multiple simultaneous mutable slices with multi-slice mute, or for array view mute, multi-slice move. I don't know that we need multiple, but that's interesting to know. We would still have to move this slice across the entire thing, right? Like this will give us one slice, but it won't give us the group of slices that we need. I want to look at the implementation of Windows for a second. Source. Is that really the source, though? Out of curiosity, would arcs let you modify the value of the window? If we used a container like a cell, we could modify the data through a shared reference. So theoretically, yes. Arcs, no, I don't think so, because arcs are reference counted types. But the cell type is meant to do that. So we could stick things in cells. I feel like the type of Windows was generic enough to support mutability, but maybe it wasn't. Squid box is a reference to a squid. If we want to have that, squid map is owned types, right? So we should be able to, if we wanted to, pass in mutable references. But Windows doesn't seem to be able to pass that through. Which is really unfortunate. I guess we could... How else can we do this? We could do it through owned types completely instead, right? We could do like squid map equals but we still need squidmap.windows still needs to be able to produce a new thing. And Windows doesn't give us any way to do that. So it lets us iterate over it, but it doesn't let us actually mutate, and it doesn't let us reconstruct that view. If we do slices, we have to deal with the bounds ourselves. Right? So if we like do a slice, let's get rid of this for a second. So we do, of course, S is going to be the thing they use. And this is going to be squid map dot slice info. And this is going to be 0, 1, 2, right? This is the same. And they had a 3-dimensional thing here, right? 1, 2, 3. They do have a 3-dimensional. So we want this, right? This gives us the same thing. So then we slice mute. And it gives us the mute squid that we want. So we can do this like this. It does mean that we have to construct these ranges for everything, right? If we have to construct these ranges, how do we construct these ranges? We do squidmap.shape, right? It's going to be an array of use sizes. So then we have rows and columns. So for 0 dot dot shape dot 0, or for row index in this, right? Is that row index or is that column index? We'll find out in a second. And then that's actually not the thing we want, right? We want for right? Because we're gonna increase by 2, I suppose. So if we start at 0, 0, we do that whole square, right? We do 3 by 3. And then that ends us with the bottom at the bottom. Okay, so we've got the counts that we need to slice to as we iterate. We need to, is it for each row? I mean, we can go down or we can go across first. It doesn't matter. So maybe we'll just do this. Right, for row index and row count. For call index in call count. Then we slice mute for row index and row index plus 2, and call index plus 2. Right? Then we have squids. And this runs forever. So this is our loop. For each of these, we get squids 1, 1, right? We match central squid. If central squid needs to flash, we do something. Otherwise, we do nothing. If squid needs to flash, then central squid equals squid flashed, right? And then if we flashed, then we have to go through everything else right now, which is squids dot iter mute maybe. Is that going to be valid? Squids.iter mute dot map increment. Wait, no. Yeah. Squid increment. Right? Did we call that increment? I forget. It's been so long since we worked on this increment energy. Right? Because squids increment energy, does increment energy set anything? It will set it to needs to flash if it needs to flash. Otherwise it increments. Why is this? This is a result or something that's yelling at me, right? I guess we don't need to map over this because we don't need to collect it. So increment energy is going to be on the actual squid here and not. Right. So that should increment if the squid flashes flashed plus equals 1. Is flash the name of the variable? Flashes. Right. So anytime we flash, we have to plus equals 1. We aren't flashing in here, so we don't need to worry about it. We can just keep track of that. Is that the right thing? We are now slice muting over all the squids. Anytime a squid needs to flash, we flash the squids around it. And then we need to check here for all squids, right? If squid map dot indexed iter dot any squid position squid match squid. Just gonna match all over the place. Then we break. And this is going to be, tell me any isn't on this actual function. Should be able to just do iter if you're not using the indexes. But iter will give me, the last time we did iter, it only gave me one of the arrays and I need all of them, right? I need all of the values. So instead of just doing like an iter over the rows, I need to do an iter over all of the squids. And I think that's what indexed iter gives us over just doing iter. Okay, so in the end, if we need to flash anything, then we return true and we keep. We could do this early. Let's do false. Well, if any of them needs to flash, we need to continue, right? So if there are none that need to flash, right, So if there are any that need to flash, this returns true. So if there are none that need to flash, then we break. And let's do debug squid map here for kicks, I suppose. Figure out what's going on. Cannot debug squid with debug. I almost wish that debug was just auto implemented. Almost. Before I forget, is that the Faithless song? No, that's someone else. Flashes. Flashes is assigned to but never used? That's not true. Why wasn't the plus equals 1 working? That was weird. Zero is unreachable because we are in the larger loop. Okay, so if we are done here with this loop, this should debug out. Or maybe I have messed up. In. We'll debug in here and out there. And let's do break because I have a suspicion. Yes. Okay. The docs suggest that iter should iterate over every value. I think only row call access only iterate over some of them. Every value for an array, though, is the values in the array, not the end values, right? The Green Velvet song. Okay, so we're panicking at assertion failed. Let's debug flashes here instead of that, because there should be a number here. Flashes equals 0. Perfect. Inner loop. How many times does this actually run? In inner loop 0. So this matches immediately, basically. And that's because what? First of all, that's got to be wrong, right? But why is it wrong is the question. This is an energy count of 9. None of these are over 10. Which makes sense. No squids flash on the first iteration. Really? What a weird... Why? Okay, fine, whatever. What's our intention then? Are we just run 100 steps? Okay. Whatever. Is this inner loop the steps? No. This loop is the steps. At which point we debug flashes. And actually return flashes too, which is the wrong type. Left 1656, right 100. Okay. Sort of a cross between the map stuff and the population modeling stuff. Yeah, fair. Get rid of squid map. We aren't resetting. That's what we're doing. We're not resetting. So after this loop, we need to do another squid map dot indexed iter mute squid, well, index squid, and then in this squid stuff we do squid.reset, right? Reset isn't a function, so expected 0 arguments. You know what? We do have to do this step. I'm gonna get some water. I'll be right back. All right, I decided against water. I decided on fizzy. Oh, I didn't decide against water. I still have water. The one thing I don't want to do on stream, dump sugary water everywhere. So the fizzy drink was a mistake. Reset. Reset is like fn reset mute self match self fill match arms. The only thing we need to do is if it's been flashed, we need to squid energy 0. The fact that that keeps being like, hey, let's throw in a mute here is really weird. Done that a couple of times now. And otherwise we do nothing, right? Self is squid energy 0. So if we go back down here, for squid in thing, squid reset. Squid reset isn't a thing because this is a tuple. So we get the squid and then we reset and then ta-da, test pass. So let's cover what we did because we got a little distracted on the mutation stuff. I wish there was a Windows mute. Why isn't there a Windows mute? That would have been so useful. Okay, so the nom parser we already did the other day. So if you're interested in the nom parser, I think we got this from day 9. And we made basically no changes to it. We basically, instead of having an option number, we constructed our own enum that is energy number, no squid for the padded squids, and then needs to flash and flashed for the state machine on whether something is flashing, needs to flash, or has already flashed. This flash symbol, instead of using the integers like U8, we get the opportunity to not break out of the U8s no matter what. So even if there's some absolutely absurdly massive number of squids all flashing, there's no way to get a number that breaks out of a U8, which is nice. We didn't even try should flash, did we? Why aren't we using should flash? Are we doing the manual number check? We did that in increment, didn't we? Needs to flash. So theoretically possible, I think, that should flash is not a thing for us. It's theoretically possible that when we construct a squid, if we have a U8 that is over 9 for whatever reason, I don't think we have that because the board setup would be really messed up if we had that. But let's make a note that squid constructed with U8 greater than 9, which breaks things, which breaks the assumptions of the board and impl functions. Okay, so should flash isn't a thing we need right now because when we increment, we automatically flip it over, right? We could use this in there. But we're already doing this, so shrug. Okay, so the squids. We go for 100 steps for whatever in 0.100. For part A of step, we increment everything by 1. For part 2 of step, which is this loop, which I will get rid of these debugs here because we don't need them anymore. For part B of step, we have to go through and first, if there's nothing that needs flashing, we're done. We break out of the loop. If we need the flash, we continually check and increment squids. So flash, increment all the neighbors, flash, increment all the neighbors, until we're done with all of the squids potentially flashing. After part B, we have part C, right? Let's label these because that seems useful. Part B. All squids. part A, increment all squids. Part C, reset flashed squids. So that gives us what we need, and then every time we flash, we're incrementing this counter right here. So we end up with the number of flashes. So let's get our puzzle input. Really, our puzzle input is like that tiny board? That feels weird, right? $17.43. That feels really tiny. That doesn't feel right. Okay, well, it works. So that's what we were supposed to do. Those numbers just feel really small. Like I was expecting a larger input. What does that even... Let's go cargo bench for part 1. It can't even take that long, can it? Nanoseconds. So like 1 millisecond, and then this is gonna be whatever. I don't know. What's the DAT profile? 3,004 4 kilobytes. 4 kilobytes. Fun. I don't know. We'll take a look at it later, maybe. These numbers seem really low for an advent of code problem. I'm just... it seems like the individual flashes aren't bright enough to navigate. However, you might have a better option. The flashes seem to be synchronizing. In the example above, the first time all octopuses flash simultaneously is step 195. If you can calculate the exact moments when the octopuses will all flash simultaneously, you should be able to navigate through the cavern. What is the first step during which all octopuses flash? This feels like it's going to be easy. I'm going to copy part 1 into part 2. I'm going to remove the function definition that I accidentally copied. Number of flashes no longer matters to us. So I'm just going to comment that out. Here, we'll do 0 dot dot for I in 0 dot dot. Right? Can we break out of this with a number? Actually, I don't think we can break out of a for loop with a number. So instead of doing all of this, let's do for each step, if all of the squids need to flash after incrementing, I suppose. And they all need to flash at the same time, right? So the first time all squids have flashed. So if we do squid map dot indexed iter dot all, don't care squid squid, match squid. Squid is going to fill match arms. We're going to be it's either going to be needs to flash, true, or no squid, true, and otherwise false. If this, then break. And we set step equals I. So let's set up the test for part 2. And this is going to be step what? $195. 195, and this is going to be step so if we run part 2, I don't want to run part 2, no, I just wanted to test it. Part 2 demo data left. Oh, that's process part 1. So 204 is the step that we get, which is the first one that is. So it's wrong. Why is it wrong? Are we doing our test wrong? We need everything after the increment to either be needs to flash or no squid. I'm doing that test wrong, aren't I? The first step during which all octopuses flash, not the first step at which all octopuses need to flash. So this needs to go all the way down here, right before we reset. And this needs to be flashed, not needs to flash. So we have 194 and the left is 195. Because they are counting from 1 and we're counting from 0. For I and 1 dot. There we go. So we'll count from 1, 2. Shrug. Seems to be the easiest. So let's run this for part 2. 364. These numbers are super small today. I expected them to be larger. Yay, I'm done. Okay, so that wasn't too hard. So we learned something interesting today, actually, is what I'll say. We reused the nom parser that we did to pull in a board of numbers into a 2D ND array vec. So a matrix, basically, for the ND array crate. Which we did on day 9. So if you are curious about that parser and how we built it, day 9 is the thing to do. And then for part 1, we basically just do each step and count the number of flashes. For part 2, we do each step. And instead of counting the number of flashes, we stop at the first one that has flashed everything. So when do we break in step 1? Just on 100 steps. So we could probably put steps in here and then have it like, yeah, I don't think we really need to abstract this. I think we could abstract like part A, part B, part C, which might make it a little bit clearer. Because we basically do part A, part B. I guess part B is this whole loop, right? No, it's not. Well, yes, it is, but we do part A, part B, part C in a loop. But we also introduce this little test here, and for the other one, we do a different range. So we could abstract this into a couple functions. It's not super necessary. But the really interesting thing we figured out today was that while Windows might not let us do mutation over like a 3x3 box across the entire set of the matrix, slices in ND-array do. So we have our 2D array here, right? And we use slice mute with the slice macro on the index +2. So we get a 3x3 at any given point. We move that around the box, and that gives us the ability to mutate over an arbitrary set of slices. So Windows is almost a specialized case of slice. And I guess they didn't do the higher order ones, or they didn't do the mutation ones, like they didn't do all of the variations, which is totally cool. But we can recreate Windows ourselves with slices. It wasn't too hard. It did take us a second, but it's possible. So we just do our own looping. And then I guess we can run the DAT stuff for part 2. It probably won't be different, right? Yeah. So they run the same. Cargo bench. Cargo bench isn't really super useful, I guess. We're only using like 4 kilobytes for this program. And the runtime is probably based on the number of steps more than it is based on the actual work we're doing. So comparatively between part 1 and part 2, I would expect part 2 to be almost double, I think, because it runs about double the number of steps. And then we have an additional check that needs to check all of the squids. So we've got about 3 milliseconds for part 2, about 1 millisecond for part 1. And that's that. Anything y'all want me to cover before we close it up? The ND array creator is really dope. I really like it a lot. And I think doing things like these slices and whatnot is really allowing me to exercise like utility of the crate. So I'll put these DAT numbers in the README, but I don't particularly think that they are that interesting. Today wasn't terrible. It was basically, we got to learn a new API for ND array. I also, I updated Rust. So you'll notice that I don't have to switch between nightly and not nightly when I'm doing these DAT profiles. Yeah, I'm definitely interested in diving into more matrix stuff with ND array. I wonder what else, like, what else do people use the ND array stuff for, right? Because like, I don't really have a lot of use cases for ND array in my day-to-day work. I guess I'm not really doing data processing that much. I'm more doing like serverless functions or like JavaScript build tools or things like that. CLI tools. I'm going to get into building desktop apps with Tori at some point when they hit 1.0. That'll be fun. Or games. Like, I guess I do games, and theoretically I could use ND array to do some game stuff. I can't think of a game that I would use it in where it would matter, though, right? Like, I'm working on a snake workshop for Rust Adventure, and like there are two choices basically for keeping the snake body around. You can either keep it in a resource and basically use like a vector queue or a vec deck and just like pop it off or add to it, or you can keep the body as components. But if you keep the body as components, it kind of has to like figure out where the other one was, kind of thing. So I don't know, like tic-tac-toe maybe would be a reason to have an ND array. But like a tic-tac-toe board is 3x3, right? So it's not like you're doing much. I guess unless you want to write some AI. If you want to write some AI, I wonder if setting up a ton of like tic-tac-toe boards as ND arrays would give you like a performance boost over just doing like Vex or something. So if you're trying to code maybe something like that, maybe AI for a board game. That, and can you tell that I've used this commit message before? So all of that is up. If you're interested in the ND array stuff, the code is there. Actually, this is day 11, so let me update that. But yeah, other than that, that's going to be it for today. I will see y'all tomorrow. Today was 11 a.m. Tomorrow is 10 a.m. So it's an hour earlier. Hopefully tomorrow is as easy as today was. I'll catch y'all around in Discord.